Hello guys, today we'll discuss some interesting concept. Now in this pandemic situation, all of you might be using tablets and mobiles for your online classes. Here I have shown one tablet with a flip-flop cover over here. In such type of cover, when you are closing the cover, automatically the screen light will get off. When you are opening it, again the screen will on. Right? So how is this happening? Today we'll discuss the theory behind this mechanism, that is Hall effect. This effect was discovered by an American physicist Edwin Herbert Hall in the year 1879. The principle of this Hall effect is when a current carrying conductor or semiconductor is placed perpendicular to a magnetic field, a voltage is developed at right angles to the current path. We'll look into this in more detail in the following slides. This current or the voltage arises due to the Lorentz force acting on the charge carriers moving inside the conductor or semiconductor. To understand this concept, I have considered this coordinate system. This direction I have taken as x, this direction I have taken as y direction, and this as the z direction. First, we'll look into an N-type semiconductor. For this, I have considered an N-type semiconductor wafer. This is the length, this is breadth, and the thickness is very small, that is a thin wafer I have taken. If we'll apply some electric field across this semiconductor, what will happen? We all know that the majority charge carriers in case of an N-type semiconductor are electrons, which are negatively charged particles. So if I am applying the electric field, these are the electrons inside the semiconductor. Automatically they will be drifted towards the positive terminal of the applied electric field. Thus the electrons are moving in the negative x direction, and due to this movement of electron, a current flows in the positive x direction. This is the direction of the current due to the electron movement. Let us now apply a magnetic field perpendicular to the surface of this semiconductor. Surface was parallel to x-axis. Now I am applying this magnetic field in the y direction, which is perpendicular to the surface of this wafer. The direction of the magnetic field B is in the positive y direction. After we apply this magnetic field, what will happen to the direction of movement of these electrons? That is determined by the Lorentz force. Let the drift velocity of these electrons due to this electric field E is given as BdE. D is drift, E is electron, and that is in the negative x direction. Further, whenever charged particles move inside a magnetic field, they experience a force given by the Lorentz force. The equation for obtaining the Lorentz force is equals to Q V cross B. Q is the charge, V is the velocity of the particle moving inside the magnetic field, and B is the magnetic flux density of the applied magnetic field. Here I have taken the velocity as VdE, and hence I have written it as VdE, and B is the magnetic field strength of the applied magnetic field. From here I can write Q is the charge of the particle, and here we are having electrons, and charge of electron is equals to minus E, so Q is equals to minus E. VdE is the drift velocity. The magnitude of the drift velocity is VdE, and it is in the negative x direction, so it is minus I cap. Cross this B vector magnitude is B, and the direction is in the positive y direction, so it is j cap. From this I can write this as minus EVdEB, and this minus I cap cross j cap. You all know the vector cross product, so I cross j is equals to K and this minus is there, so it is minus K cap. So the Lorentz force is equals to minus EVdB minus K cap. Further this minus and this minus they will go and I can get Fm is equals to EVdEB K cap. That means the force experienced by the electrons due to the magnetic field is in the positive z direction. So this is the Lorentz force experienced by these moving electrons due to this applied magnetic field. When this magnetic field was not there, they were experiencing a force in this direction due to this electric field over here. Now they are getting one more force in this direction. The resultant will be somewhere in between. Here we will get the resultant. So the direction of the resultant force will be somewhere in between this, and due to that resultant force these electrons will now change their path. They will move in a parabolic path. So this will be the path of the electrons after the application of the magnetic field. Thus, these electrons will try to move towards this front face. This side I am calling the front face and the other side I will call it as back face. So, these electrons, due to the application of the magnetic field, now they will try to move towards the front face. This is what we have seen. The Lorentz force due to the magnetic field is equals to EVdEB K cap, and the electrons will try to move towards the front face. So slowly they will move towards the front face. How can we know that? What is the distance they will move? Where they will stop or they will move indefinitely? Let us look into that. When these electrons are moving to the front face, they will leave positive ions at the other side, that is the back face of the wafer. So the positive ions are left at the back face and the electrons they moved to the front face. Now these are positively charged and the electrons are negatively charged. So obviously there will be some force of attraction between these positive ions and negative electrons. What will be the direction of that attraction force? Obviously it is in the negative z direction. These are immobile ions, so they will try to attract these electrons in the negative z direction. The Lorentz force was in the positive z direction, and this force due to the positive ions are in the negative z direction. So now there are two forces acting on these electrons, one in positive z direction and one in negative z direction. So they cannot move indefinitely. They have to come to rest at some point when these two forces will balance each other. Right? So that condition is known as equilibrium. So at equilibrium, the magnitude of this Lorentz force should be equals to the magnitude of the force experienced due to the positive ions at the back face. At that situation, there will be an equilibrium between these two types of charges and we will be getting some definite voltage between the front face and the back face. Thus, if you will connect some voltmeter between the front face and back face, we will be getting some readings over here, and that reading in the voltmeter is known as the hall voltage and denoted by the letter VH. So VH is the hall voltage over here. This side is positive and this is the negative. Further, these are positive ions and these are electrons. So this side is positive and this side of the wafer is negative. And hence, there will be an electric field between the back face and front face that is given as EH. And this is transverse to the plane of the wafer. This EH is known as Hall field, which is due to this Hall voltage, and it is transverse. So EH is the transverse electric field due to Hall voltage. Now we'll look into P-type semiconductor. Here this is a p-type semiconductor, and in p-type semiconductor, holes are the majority charge carriers. So if I am applying an electric field, these holes will move in the positive x direction, as this is the negative terminal of the applied electric field. And we all know that the direction of current is same as the movement of electron. So this is the direction of the current, which is again in the positive x direction. Thus, the drift velocity of hole due to the applied electric field is given as VDH, and its direction is in positive x direction. Now, if we are applying a magnetic field perpendicular to the plane of the wafer, that is in the positive y direction, what will happen? Let us look into that. As these holes are moving inside a magnetic field, they will experience a Lorentz force given by the equation Fm is equals to Q VDH cross B. Q is the charge of the moving particle, that is charge of hole. So Fm is equals to charge of hole is equals to cross E. VDH can be written as the magnitude is VDH and direction is positive x direction, that is I cap. B vector can be written as B, the magnitude, and J cap is the direction, that is in the positive y direction. This can be arranged like this: E, V, D, H, B, these are the magnitudes I kept together, and the vectors are I cross J. The vector product of I cross J is nothing but K cap. Thus, Fm is equals to E, V, D, H, B, K cap. That is the Lorentz force on these moving holes is in the positive z direction. This is the Lorentz force which is in the positive z direction. This shows that after the application of the magnetic field, these holes are experiencing two forces, one due to this applied electric field which is in the positive x direction, and the Lorentz force due to the magnetic field is along the positive z direction. So if I am taking this as the force direction due to the applied field and this is due to the applied magnetic field, there will be some resultant force coming in this direction. So if the resultant force and the holes are coming in this direction, that means this will experience some force in this direction, and hence it will move in a parabolic path. So this will be the path for the movement of holes after the application of magnetic field. Earlier it was moving straight, now the path has changed to a parabola. Due to this resultant force, these holes slowly they will move towards the front face. So they are slowly moving towards the front face. When they move to the front face, they will leave negative ions at the back face. So at the back face we are getting negative ions accumulated and the holes are coming towards the front face. These negative ions, they will attract these positive holes. That means the holes are also experiencing an electrical force due to these negative ions, and the direction of that is in the negative z direction. Due to this force, these holes cannot move indefinitely. They have to come to an equilibrium, and at equilibrium, the magnitude of this Lorentz force should be equals to the magnitude of this force due to negative ions. Once the equilibrium is established, we are having positive holes at the front face and negative ions at the back face. Under this condition, if we will connect a voltmeter between the front face and the back face, it will give us some reading in the voltmeter, and that voltage is known as Hall voltage and represented as VH. Further, we will be having a field between this front face and back face because of these positive holes at the front face and negative ions at the back face, and that field is known as Hall field, which is given as EH. The direction of this Hall field in case of a p-type semiconductor is from front face to back face. Let's compare the two types of semiconductors we have discussed. This is for n-type semiconductor. we have seen the electrons are coming to the front face and the positive ions are getting accumulated at the back face, due to which we are getting a potential difference between the front face and back face, which is denoted as VH. This VH is known as Hall voltage, and there is an Hall field, and the direction of this Hall field is from back face to front face. So this EH is the transverse electric field due to Hall voltage. Now coming to the P-type semiconductor, here the positive holes are coming towards the front face and the negative ions are getting accumulated at the back face. Thus the Hall voltage we are obtaining in case of P-type semiconductor is just opposite to that of the Hall voltage in case of an N-type semiconductor. And due to this Hall voltage, again we are getting a Hall field, and the direction of Hall field in case of a P-type semiconductor is from front face to back face, that is negative Z direction, but in case of N-type it was in positive Z direction. For reference, I have given the coordinate axis over here. This is the theoretical concept. We will do the derivation for Hall voltage and Hall coefficient in the next video. Today, before winding up, let us see what are the uses of this Hall effect. This is used to identify the polarity of charge carriers in a material. Just now we have seen that depending on the charge carriers, the polarity of the Hall voltage changes, and hence this can be used to identify the polarity of the charge carriers. Further, this can be used to find out whether the material is P-type or N-type semiconductor. To calculate the drift velocity of charge carriers, this can also be used to calculate carrier concentration and mobility of charge carriers. We'll look into the details for these calculations after the derivation of Hall voltage and Hall coefficient. Let us look into the question I asked in the beginning. Why this screen is getting off when we are closing this, and why the screen is getting on when we are opening the cover. This was the question, right? So a Hall sensor is mounted inside the cell phone and a magnet is there inside the cover. So whenever that magnet is coming in contact with the Hall sensor, there that Hall voltage is getting developed, and that Hall voltage is creating all this magic. So today we'll stop here. Thank you all. If you like the content of the video, please subscribe to the channel, and also don't forget to press the like button and share the link with your friends. Thank you all.